Welcome to this video on forces on inclined planes. In this video we're going to be taking a look at how to analyze the motion of an object that's not on a flat surface. And we're going to jump right in by placing a little box on this inclined surface. Now we would describe the incline of the surface, basically how steep it is, by this angle over here. And this angle is the angle from the horizontal, or the angle from, if it were flat, it would be measured from that x-axis. Now I'm going to start by drawing a free body diagram here, and I'm going to think about what forces would be acting on this block. Now if this little block or box is at rest, it would have slightly different proportions of the forces than if it is moving at a constant velocity / accelerating. Now what I'm going to start by saying is that this object has mass and therefore is attracted to the Earth through the force weight, or mass times gravity. And we know that that force is always points towards Earth's center. So we know that it has to go straight down. And when we had a situation where the object was on a flat surface, that force was perpendicular to the surface. But now that the surface is inclined, that's not necessarily going to be the case. We know that it has the surface pushing up on it, but normal forces, as the name suggests, these surfaces are always perpendicular to the surfaces that are in contact. Now we know that this box would most likely, from our experience, just slide down the ramp if there was not enough friction pointing in the opposite direction. So I'm going to go ahead and draw this friction on here, and I'm going to label it static friction. And we know from our previous studies of frictional forces is that they're parallel to the surfaces that are in contact. So at this point we need to make a couple of adjustments to the way that we would write net force or force summations statements or equations. Because before, what we would say is if something was at rest, then it had all of its forces balanced. And if something is not at rest, it could be at a constant velocity, in which case its forces would be balanced still. But if it's accelerating, then its forces would be unbalanced. Now we know that this object is at rest, just based on what I decided for this situation. So that means that the forces have to be balanced. Well, none of them are pointing opposite one another. So now we have to kind of reevaluate how we analyze these situations. So we know that if this thing's at rest along this parallel line along the surface, we know that the force friction has to have another force pulling this way that has to have the same magnitude and opposite direction to the frictional force. We know that if this box isn't sort of tipping off of the incline or going into the incline, then it needs to have some force opposing the direction of the normal force, and those need to be equal to one another. So that leaves us with kind of an issue, because we know that there may or may not be any forces that are actually acting down the ramp or into the ramp. Well, it turns out that these are just components of the weight of the object. So the way we would describe that is we'd say that some of the weight would cause the object to get pulled down the ramp. So gravity, the effects of the gravitational force have two sort of parameters to them. One of the parameters is how much the force pulls down the ramp, and the other one is how much the force is pushed into the ramp. So when we look at these two arrows, the red ones that I've drawn over here, what we're going to label those are components of the force weight. So I'm going to go ahead and write in here that this component is going to be called the weight perpendicular component, and this one is the parallel component of the weight. Now the reason we're calling them perpendicular and parallel is because they're perpendicular to the surface or parallel to the surface. So now I can step to the side here and actually try to write out a net force equation or a force summation. So I can say that mg parallel minus the force of friction equals 0 net force. In other words, the mg parallel component is equal to the static friction component, and that's why the object's at rest. We can also say that the normal force minus the mg perpendicular component has a net force of 0, or in other words, the normal force is equal to the weight component pointing into the incline. So just to think about it in a more logical way, if you have an object on an incline, the weight is pulling it straight down, but because of the angle of the incline, that weight is sort of broken up into two components. One of those components is pulling it down the ramp, so we'd see it as being pulled down the ramp, and the other component is pushing it into the ramp. And because of that, we have to adjust the way that we label the force weights in the perpendicular dimension and in the parallel dimension. Now, some people still refer to the parallel dimension as x and the perpendicular dimension as y, but you can see here that that's not going to fit our regular Cartesian system, and so that's why we don't necessarily need to write it that way. You can, however, think of the Cartesian coordinate plane as being rotated, and that the x-axis is parallel to the surface, and then you get the same defined values as parallel being x and perpendicular being y, but you don't need to worry about that necessarily. Next up, what we're going to do is take a look at how do we actually calculate the amount that mg perpendicular and mg parallel make up.